Hi, in this video, hold on a second, looks like my camera's not focused. Let's try that. Okay, in this video we're going to be talking about the difference between exponential growth and exponential decay. So what I want you to point out is from that first video is you'll notice that as we graphed this and we made a little t-table that the graph started off and it went through 0, 1, that most important point, and then it went and shot upward, right? And this is called an exponential growth function. Why is it growth? Because we can see that the thing is getting bigger, it's getting higher, right? Let's look at what happens though if we take and we put something like f of x is equal to 3 to the negative x. What if that's a negative exponent? Okay. Well, what I'm going to do here is I'm going to go ahead and build a little t-table. Okay. And let's just put some values in. And let's figure out what would happen if I put these different values of x in to my equation here. Let's start with 0. Okay, because that's the easiest one. If I put 0 in, that's 3 to the negative 0 power, and we know that that's 3 to the 0 power, and anything raised to the 0 power, if you watched the previous video, is 1. So my most important point is still at 0, 1. What happens if I put a 1 in, though? Well, if I put a 1 in, now I get 3 to the negative 1 power. And if I put 3 to the negative 1 power in, if you watched the previous video, you know that that's actually 1/3. So I'm dividing by 3 in this case. In other words, I'm going to get 1/3 out, and it's going to be a point that looks like this. So you'll notice that it already looks different, right? It's not shooting upward. Now it looks like it's going down. If I put a 2 in, that's 3 to the negative 2 power, which is 1/3 squared. So really, that's 1/9. If you watched the previous video, that looks pretty familiar, right? So 2 gives me 1/3 squared, 1/9. That's going to be like right here. If I put 3 in, same idea, gives me 1/27th. 1/27th. And so I get, man, I'm getting really close to that axis, aren't I? But it looks like I'm never going to touch it. In fact, if I put 10 in, I'll be at 1/59,049. How did I know that? Because I did that in the previous video, right? And so what happens is the negative sign is thrown in. It's like these fraction things we're doing, except the negative sign is already up there. So I'm like really close to 0, but I'm not touching it on this side. And what happens if I put a negative 1 in now? Okay, let's go the other direction. If I put a negative 1 in, all of a sudden I'm talking 3 raised to the negative 1 power. You'll notice that that is a double negative, right? So that's 3 to the first power, which is just 3. So negative 1, positive 3 becomes a point on my graph. If I put a negative 2 in, let's just change that to a negative 2. Now it's a positive 2, right? Because it's a negative 2. Double negative gives me a positive 9. And then the next one would be 27, and I'm off the graph because 3 cubed is 27, you know, way out there. So I'm done. And what you'll notice here is a function that looks like this instead. And it starts to go to 0, but it never touches it, right? We call this kind of function, when it looks like this, decay. Okay, that's an exponential decay function. And what it means is that the amount of whatever I have here is dying off, but it never quite goes away. So here's the application that we're going to see in a few days, okay, when we're working on word problems. Exponential growth is going to be something like a bank account problem. I put money in the bank, and the money grows over time. And that money, it turns out, grows exponentially. Okay? It's really nice whenever we start to get into this function. Unfortunately, you're going to find out that most of the time your growth is like this. Okay? It's in that part of the graph. But growth is something like a bank account with interest. Okay? Decay is going to be something like radioactive decay, where we have some amount of a substance and it dies off, it turns into something else. Or perhaps a more common one is going to be something like you buy a car, how much is the car worth? The instant that you drive that car off the lot, it drops a lot in value. And then over time, it still loses value, but it doesn't really quite lose all of its value, and it never quite loses all. I mean, you never have a car that's worth $0. You can sell it for $5 if you wanted to. But if it was 100 years old and a pile of rust, you know, you're not going to get much out of it. So that would be an example of a decay problem. And really the idea is this. Does it go up as it goes to the right, or does it die off and go to 0 as it goes to the right? One is growth, and the other one is decay. Hopefully that makes sense. You're going to have a chance to play around with different things, like what happens if I do 1/3 raised to the x power. Okay, what's that going to look like? Is it growth or decay? My suggestion to you in a problem like that is to simply go like this. Go into your graphing mode of your calculator. Go y equals use parentheses, that's very important, 1/3 raised to the x power. Is this growth or decay? Let's take a look. That looks like decay to me. That's a decay problem. Okay, so if all else fails, we'll just plug that in. We can also go to the table, right? And we can use the table to quickly get those values. Oh, look at that, 27, 9, 3, 1, 1/3. I bet that's 1/9. I bet that's 1/27. I bet this is exactly the same thing as what we saw here, right? And so you'll use your calculator, in other words, to get the t-table to be able to plot some points and be able to recognize, is this a growth or decay problem, simply by typing it in and using parentheses. So hopefully that makes sense. That'll get you really going on the homework today, and we're flying along. We'll be able to talk about asymptotes in the next video, which is going to be this important concept of, hey, you know what? It comes close to 0, but never touches it.